Today we're going to study definite integrals and antiderivatives. Unlike an indefinite integral where you're not sure about beginnings and ends and if there's a constant added, these actually have numbers on your integral sign, so you'll have an upper and lower limit. So we're going to go through some properties for definite integrals. The first is order of integration. Order matters in math. And so if we're starting with an integral here, a to b of f of x dx, what we see is that the a and the b are in the wrong order, which means you're starting at a larger number and moving left on your number line when you should be starting at a, the smaller number, and moving right on your number line. So to correct this, we just change the sign. So make it a negative, switch a and b, and that will correct our integral. Now the zero integral, a lot of what we're talking about, we started with talking about distances. So zero rule. If you start at a, remember a is an x value, and end at a, you haven't gone anywhere. You haven't traveled, so there has been no distance traveled. So this integral gives you 0 for an answer. Much like derivatives, if you have a constant or coefficient in front of your equation, then you just leave it, and we just act like it's not there and multiply it towards the end. So if we have a constant k multiplied to our function prior to taking the integral or the antiderivative, what we can imagine doing is moving the k to the front and then multiplying it by the antiderivative. Okay, same type of thing with derivatives. When we're taking a derivative and it has multiple terms, what we look at is that we're actually going to take that derivative of each piece. So you can actually look at many of our equations as having multiple functions inside just simply because they're added. And what you can do is just separate it and look at it piece by piece. And I left an important part of notation off here. dx. I'm going to run out of space, so I'm going to come down here below. So f of x dx plus or minus g of x dx. So that's just saying sometimes you have multiple pieces like we did with indefinite integrals. Okay, additivity means if you have the same function and so we've got from a to b, and we're going to pick up at b and go to c. And it has to be the same function. It can't be two different functions. What that means is that you can combine these two intervals to make it one large interval and take it from a to c, like this. And that's called the additivity rule. For our first example, I'm giving you three definite integrals. They're definite integrals because we have values for a and b and what their value is. And basically we're going to substitute appropriately, but we're going to use our rules. So if you look at part A, I have an integral from 4 to 1 of f of x dx, but your 4 and your 1 are in the wrong order. The smaller number is supposed to be on the bottom in the A position. So what the order or integration rule tells us is that we can take the negative and switch the limits of integration and put them in the correct order. Now what we see is that we're going to try to match this up. What I see here is that this integral from 1 to 4 of f of x dx is right here, and that its value is negative 2. So we're going to keep this negative out here. That counts as our k as a multiple. and then we will just fill it in. So we keep our negative, put in the value, and then our answer is 2. Now the next one, part B, the limits of integration are in the correct order. -1 is smaller than 4, and it's the bottom where it belongs. And so we need to look and see if we have a integral that goes from 1 to 4. Well, we have one that goes from -1 to 1, and we have one that goes from 1 to 4. Since this one here and this one on the second one matches, and also the most important, it has to be the same function. You can't, in some situation like this, you can't combine it with an h. So what we're going to do is split up this large integral from -1 to 4 into the two small integrals that we do have. So we're going to take this one from -1 to 1, and then we're going to do the other one from 1 to 4. And then we'll combine them, because we know the integral from -1 to 1 of f of x is 5. And we know the integral from 1 to 4 is -2. And that gives us 3. And I'm going to show you how to visualize this on a number line in just a minute. Okay, part C. I have integrals from -1 to 1 at 2 times f of x plus 3 times h of x. Well, what we can do is split this up and pull those coefficients 2 and 3 to the front. So I'll say 2 times -1 to 1 of f of x dx plus 3 times -1 to 1 of h of x dx. And then I need to check and make sure I actually have values for that. And I do. This one right here matches the first integral. And this one with the h matches the third integral. So I'm going to keep my coefficients. 2 times 5 plus 3 times 7, we just substitute. And that's 10 plus 21, which gives us a value of 31. Okay, for the last one, let's look at this one. Our limits of integration go from 0 to 1 for f of x. So I'm checking both of my f of x's. And I don't have a 0 to 1, and I don't have any way to identify what. If I knew what -1 to 0 was, I could subtract that out, but I can't do that. So this particular one, not enough information. To expand some information for you on 1b, where you combined the integrals, I want to show you a way to look at this on a number line. So we're going to say that we have from -1 to 4, the number line is going to represent our function, and we don't know what this is. But if we look at the two integrals that I gave you on the previous example, at 1, we know that from -1 to 1, the value is 5. And we know that from 1 to 4, the value is -2. What you're going to do to combine these is you're just going to add the two values. So sometimes it helps to look at it at a number line. If we were to subtract them, then let's see, if we ended up knowing that we had a smaller, a bigger interval, and we were looking for portions of another one, we're going to do that example next. Okay, for this example, I've got two integral values for f of x, and one of them is larger than the other one. I have one that goes from 0 to 4, and then one that goes from 2 to 4. And so I'm going to use that information to find the value of 0 to 2. So what you can do, if you like the algebra version, is you can take the larger interval, 0 to 4, and subtract the other one, the 2 to 4. And that what that leaves you is the integral from 0 to 2. And then we would substitute our information and get negative 10. Now, another way to look at this is to use a number line. And we know that 0 to 4, the whole thing is negative 3. And we know that 2 to 4, the whole thing is 7. And so this integral is what we're looking for. We'll call it x. So we'll say x plus 7 equals negative 3, and x is negative 10. So you can either do it algebraically, or you can look at it on the number line. What we're going to begin doing now are definite integrals using antiderivatives. And unlike the indefinite integrals, you do not add c. We're going to evaluate this and get a number. So what we're going to begin looking at is this 2x. What did we take the derivative of to get 2x? We got x squared. Now, once you take an antiderivative, you don't need the integral sign or dx anymore. Those are symbols that mean that we're working with a derivative. But what we are going to do is draw a little line, and it's going to show me that I need to evaluate this problem. My answer is going to be a number. And so what I'm going to begin doing is you always plug in the larger number first. So we're going to substitute 2 into x squared. So we'll have 2 squared. Subtract always, and then we plug in the 1. And so that's 4 minus 1, and that's 3. So we're also going to begin looking into problems with trig problems, and we're going to use some of those, but let's do another one first, and then we'll get into a trig problem. So I'm going to take the integral from 0 to 2 of x minus 1 dx. Now remember, the integral sign and the dx are a sign that we have, we're working with a derivative, and we ask ourselves, what did we take the derivative of to get x minus 1? Well, the rule says we add 1 to our exponent, divide by the new exponent. Same thing with the 1. And there we go. And we've got to evaluate this. We haven't yet. So this symbol basically is telling me I want to plug in 2, and then I'm going to subtract and plug in 0. So I'm going to start with plugging in the 2 because it's bigger. So I've got 2 squared divided by 2 minus 2, all in parentheses. And then we're going to go through the motions of plugging in 0, because sometimes you actually don't get 0 when you do this. But we're going to do that. And then we're going to simplify this, and that's 4 divided by 2 minus 2. And this actually does give me 0 for an answer, which means part of my equation's above the axis and part of my equation's below the axis, and they canceled. But this is our answer. Okay, for this example, we need to take the antiderivative, and we raise our exponent by 1, divide by the new exponent. Now we have this 4. You can leave it alone, but what you can do is say I'm going to raise my exponent by 1 and divide by it. But 4 divided by 2 is 2. And then we have plus x. So from 0 to 3, we plug in. Always plug the 3 in first, it's bigger. So 3 to the 4th power, that is 81. And 2 times 9 is 18, and then plus 3, all in parentheses. Good habit. Plug in a 0, all you get is a 0. Now, I'm not so much on automatically going to decimals, so please don't do that. And do go ahead and simplify this. And when you simplify, find a common denominator, you'll end up with 21 over 4. And just leave it as a fraction. Okay, I have last example, the integral from negative pi over 2 to pi over 2 of cosine theta d theta. Now it does not matter what the variable is, as long as this one and this one match. So what we took the derivative of to get cosine is sine. So sine theta. So we're going to evaluate this from negative pi over 2 to pi over 2, and then plug them in one at a time. So you've got sine of pi over 2 minus sine of negative pi over 2. Now, what I don't want you to do is plug this in and keep your calculator in degrees. You need to plug this in, if you are plugging it in, and put your calculator in radians. But what I happen to know is that the sine of pi over 2 is 1. And I also know that the sine of pi over 2 is negative 1. And this gives me positive 2.